Good morning, my dear students. In the previous class, we discussed about the potential energy of the dipole in the uniform electric field, and we derived the expression for that, and we get the potential energy U is equal to minus of Pe cos theta, where P is the dipole moment, E is the electric field, and theta is the angle between the dipole and the electric field. Today we will talk about the behavior of the conductors in the electrostatic field or electric field. We know that these conductors are nothing but the substances which carry the charges. There are so many free electrons, and these free electrons are moving randomly inside the conductors, so they can carry the charges or the electric current. When these conductors are placed in the electrostatic field, they place an interesting phenomenon that we are going to be discussed in this class. So here, as I say that when the conductors are placed in the electrostatic field, their behavior is different. And how does the conductor behaves in the presence of the electric field, that we will see here. Say that the first point of this conductors when the placed in the electric field is, say that net electric field in the interior of the conductor is 0. This is the first point. Net electric field, I write here net electric field in the interior of the conductor is 0. Net electric field in the interior of the conductor is 0. What this statement means? Say that there is a conductor, and this conductor is placed in the presence of the electric field. When this conductor is placed in the presence of the electric field, say that there is a electric field. This is the electric field, and in this electric field I have placed a conductor. Then what happens? Inside the conductor, the charges get accelerated with their opposite kind of the charges. Say that we know that in the conductor there are positive and negative charges. These positive charges and negative charges get separated. Say here, either one side of the conductor I will get a negative charges, in the other end of the conductor we get the positive charges. So these positive and negative charges establish the electric field. These positive and negative charges establish the electric field now, and whatever the electric field is established by this conductor is in the direction opposite to the applied electric field. So the electric field established by this conductor cancelled by this electric field whichever way applied. Therefore, electric field inside the conductor is 0, because what the electric field we are applied is cancelled by the electric field established by this conductor, because they are equal in magnitude and opposite in direction. So these conductors produce the electric field in a direction opposite to the applied electric field, hence they cancel out, therefore the electric field inside the current inside the conductor becomes what? 0. That is why we say that net electric field in the interior of the conductor is 0. Electric field inside the conductor is always 0. This is very important. This is the one point, that net electric field in the interior of the conductor is 0. Right. So the next point, say that electric field just outside the charged conductor. I will write the second point here. Electric field this is the second point. Electric field just outside the charged conductor electric field just outside the charged conductor is perpendicular to the surface of the conductor, is perpendicular to the surface of the conductor. See here, electric field just outside the charged conductor is perpendicular to the surface of the conductor. We know that electric field is always perpendicular to the conductor. We have studied in the properties of the electric field lines. Suppose I'll draw here, there is a conductor and it is a charged conductor, then electric field is perpendicular to the surface of this conductor. This is the E. Electric field is always perpendicular to the surface of this conductor. Why this is always perpendicular to the surface of the conductor? Electric field just outside this charged conductor is always perpendicular to the surface of this conductor. Why? Because we know that E cos theta must be equal to 0. If suppose that electric field is not perpendicular to the surface of the conductor, then there must be the component of this electric field. Say that here must be the component of the electric field. If electric field is not perpendicular, then there must be the component of this electric field. Say that it is E cos theta and it is E sin theta. Say these are the positive charges. Right. So if there is a component of the electric field, then there must be some value of the electric field. There must be some electric field is present now. If there is electric field is present, we know that charge in the presence of the electric field experiences the force. Any charge in the presence of the electric field experiences the force. Then this charge present on the surface of the conductor experiences the force. So that starts moving now. That starts accelerate. So this charge is moving further now. If this charge is moving in this direction, then there is one more charge present here. So these two charges repel with each other. So they starts repel. So this charge is moving further. So because of there is another charge present, this charge experiences the force now. Force of repulsion. Like that, these charges started experiencing the force now in this direction. Like this. So these charges experience the forces now. These charges experience the forces means what? These charges are now moving in a particular direction now. So if the charges are moving in a particular direction, it means that there must be some surface current is available. There must be some surface current is available. So which is not possible, which is not true. That is why electric field is always perpendicular to the surface of the conductor. When it is perpendicular to some conductor, then only cos 90 must be equal to 0 if theta is equal to 90 degree. If theta is equal to 90 degree, we know that E must be equal to 0. Right? So electric field just outside the charge conductor perpendicular to the surface of this conductor. Every time the electric field must be perpendicular to the surface of the conductor. Otherwise, if it is not perpendicular to the surface of the conductor, then there must be some current is available. Alright? So that is why if the surface current is available, then we cannot say that it is true. So surface current, to get the electric field perpendicular, then there must be electric field must be equal to 0. That is why I said that electric field in the interior of the conductor is 0. Remember that electric field just outside the charge conductor is perpendicular to the surface of the conductor. This is the most important. Right. Then third one, you say that net charge in the interior of the conductor is 0. Third one I will write here. Net charge in the interior of the conductor is 0. Net charge in the interior of the conductor is 0. It means what? The charges are temporarily separated. The charges are temporarily separated as I shown earlier. If they are temporarily separated, the total charge on the system must be equal to what? 0, as I shown here. The charges are temporarily separated. If they are temporarily separated, then the total charge of the system must be equal to what? 0. That is why the net charge in the interior of the conductor is what? 0. This is also very important, that the net charge in the interior of the conductor is 0. And using this, we can say that the fourth property, charges always resides on the outer surface of the conductor. Charges always resides on the outer surface of the conductor. Outer surface of the conductor. Charges always resides on the, resides means what? They are kept on the surface. This is the conductor supposed to be say that, and we know that charges were always present on the outer surface of this conductor. There are no charges present inside the conductor. That is why electric field inside the conductor is 0. All these 3 points are related with the 4th point. We say that net electric field is 0. Why? Because there are no charges are present inside the conductor. That is why charges always resides on the outer surface of the conductor. Since the charges are resides on the outer surface of the conductor, electric field just outside the conductor is perpendicular to the surface of the conductor. In the properties of electric charges also we have said that charges always resides on the outer surface of the conductor. That is why electric field is perpendicular to just outside the surface of this conductor. Okay, so this is the 4th point, and the 5th point is very important here. Fifth point says that electric potential is constant for entire conductor. Electric potential is constant for entire conductor. Electric potential is constant for entire conductor because of, say that we know this is the conductor, and we know that charges are resides on the outer surface of the conductor. Why we can say that electric potential is constant for the entire conductor? For this entire conductor, electric potential is constant. Electric potential constant means what? dV must be equal to 0. Say that there are 2 points. This is point 1, point A, this is point B. If I suppose to be take a charge Q, and I will bring this charge Q from point A to the point B, point A to the point B, we know that electric field inside the conductor is 0. Net electric field in the interior of the conductor is 0. We know this is. If I suppose to be move a charge from point A to the point B, I am proving that electric potential is constant on the entire conductor here. We know that on the surface of the conductor here potential is same. Now here if I bring the charge from point A to the point B, I have to do some work here to bring that charge. Alright, so work done to move a charge from point A to the point B against the electrostatic field we have studied. Since there is no electric field, if there is no electric field, then there is no work done. Work done is 0. So we say that here we write WAB by Q is equal to VB minus of VA. VB minus of VA. We have studied that because work done to move the charge from point A to the point B in the electric field. Now there is electric field is what? 0. Electric field is 0. So electric field 0 means what? Work done is 0. So this becomes what? 0. So it is VB minus of VA. Or we can say that VA is equal to VB. So electric potential at point A and at point B is same. So the electric potential is constant for the entire conductor because there is no work done. Why there is no work done? Because electric field inside the conductor is 0. So then there must be no work done to move a charge. Alright, so this is the 5th point, and these 5 points are very, very important. It shows that how the conductor behaves in the presence of the electric field. Okay, in the next class we will talk about the electrostatic shielding dielectrics. Okay.